Hello, so I'll be looking at energy stored in a capacitor. We previously looked at capacitors, combination of capacitors, capacitance of a capacitor, and so this particular lecture addresses the energy stored in a capacitor. We've earlier mentioned in my previous lecture that a capacitor is a device that stores electric charges. So we just simply say a capacitor is used to store charges. Now, the energy stored by a capacitor is expressed as the work done in charging that capacitor. And mathematically, we have some expressions to represent the work done in charging a capacitor, or simply the energy stored by a capacitor. We have W is equal to half, that's 1 over 2 times Q squared over C, where Q is the charge. We also say W is equal to 1 over 2 QV, and W is equal to 1 over 2 CV squared. W is equal to 1 over CV squared. All three equations can be derived, but this particular lecture will not be addressing that. In the formulas that were given, W is the work done in charging the capacitor, or simply the energy stored by the capacitor, and the SI unit is joules. We have Q as the charge in coulomb. C is the capacitance of the capacitor, and V is the potential difference in volts. You also need to take note of this point, that the work done in charging a capacitor can also be expressed or considered as the potential energy stored in the capacitor. So let's move on. So having looked at energy stored in a capacitor, recall from my previous lecture that I mentioned that a dielectric material can be placed between the parallel plates of a capacitor. So let us look at capacitors with dielectrics. Capacitors with dielectric. Now, this dielectric material or dielectric materials, they are materials that do not conduct electricity. Okay, so they are non-conducting. An example or examples of dielectric materials include glass, rubber, etc., etc. This dielectric material that is placed in between the plates of a capacitor has some advantages, and these advantages, some of them are: number one, the dielectric material that is placed in between the parallel plates of a capacitor helps the capacitor to increase the capacitance. It helps the capacitor to increase its capacitance. Also, the dielectric material can help to improve the voltage of the capacitor, and it also helps in improving energy storage by a capacitor. So these are some of the notable examples of dielectrics in capacitors. Let's move on. So looking at capacitors with dielectrics, We have said previously that one notable advantage of a dielectric material is that it helps to increase the capacitance of a capacitor. In that case, when this dielectric material increases the capacitance of a capacitor, it does that by a constant. We call that constant K. And the constant has no dimension, meaning it is dimensionless. Recall that the capacitance of a capacitor, we expressed it as permittivity of free space times the area all over D. But when you have a dielectric material involved, the capacitance is increased slightly by that dielectric constant, which is K. So that gives us this expression for capacitance with dielectrics. And in this case, our K is the dielectric constant, A is the cross-sectional area of the plates, D is the distance separating the plates, while A naught is the permittivity of free space. So we move on. I have two capacitors. One is 200 microfarads and the other is 400 microfarads. They are both connected in series. Now we have a potential difference of 7 volts that is connected across the capacitors. We are told that the potential difference is provided by a battery, and that battery has negligible internal resistance. So the questions are: calculate the charge stored by the 200 and 400 microfarad capacitors respectively. And part B says calculate the potential difference, that is PD, for each capacitor. Now, we need to know that, or we have to recall that capacitors in series, they are characterized by the same charge flowing through. Assuming we have, let's just give a sketch here. I'm gonna wipe it off. This is a capacitor. This is another capacitor. Connected to a potential difference. Now, if this is, let's say, the 400 microfarads, this is 200 microfarads, and this is the negative terminal of the battery, this positive terminal, this is V. If charge leaves this battery, the same charge that enters if charge leaves the battery, the same charge will flow through the 200 microfarad and the 400 microfarad. Why? Because they are both in series. However, they will have different voltage, that is, they will be maintained at different voltage. So When the question says calculate the charge stored by the 200 and 400 microfarad capacitors respectively, we have to remember that both capacitors will carry the same charge. So the first thing to do is to calculate the equivalent capacitance. Then before we now find the charge flowing through the capacitors. So let's proceed. I'm going to wipe this off. So I'll recall that Q is equal to CV. C is the capacitance and V is the voltage. So for series connection, in series, we have same charge. So that we can find the total capacitance as remember, for series connection, the total capacitance is obtained using the reciprocal law. So we say 1 over total capacitance is equal to 1 all over the 200 microfarads plus 1 all over 400 microfarads. This gives us, as a common factor, 400 microfarad. This into this gives us 2. 2 multiplied by 1 is 2. 400 into this is 1. 1 multiplied by 1 is 1. So we have this is equal to 3 all over 400 microfarads. That leaves us with the total capacitance as 400 microfarads divided by 3, and that leaves us with 133.33 microfarads. Of course, since they have the same charge flowing through them, then we use the equivalent capacitance to calculate for their charge. So from this equation, we'll now say Q is equal to the total capacitance times the voltage, which will now be equal to 133.33 micro is times 10 to the power minus 6. So say multiply by 10 to the power minus 6 farad times 7 volts. This leaves us with 9.33 times 10 raised to the power minus 4 coulomb. For part B, we have to find the PD for each capacitor. Since they are in series, they will have different potential difference. So for the 200 microfarads capacitor, we say V is equal to, from this expression, V will be equal to Q over C. So we say Q over C, which is each of them has charge 9.33, so we say 9.33 times 10 to the power negative 4 coulomb divided by C, 200 times 10 to the power negative 6 farad. This leaves us with a potential of 4.665, which can be approximated to 4.67 to 2 decimal places. Then for the 400 microfarad capacitor, we have Q over C, which is 9.33 times 10 to the power negative 4 coulomb divided by 400 times 10 to the power negative 6 farad. This leaves us with a potential of 2.33 for 333 V. If you check and add both of them, it will give us approximately 7 volts. Add this to this, we will get approximately 6.998 volts, which approximate to 7 volts. So we are correct. Let's take another example where we'll have to look at a capacitor that has a dielectric material. Here we have a 2 parallel plate capacitor with dielectric constant 2.3. We are told to assume that the plates are separated by a distance of 1 centimeter with cross-sectional area of 200 cm squared. The constant potential difference is 3000 volts. We are expected to find the capacitance of the capacitor, the charge flowing through the capacitor, the work done in charging the capacitor, and the new energy stored in the capacitor if the PD is tripled and the capacitance remains constant. So let's proceed. First, we have that K, which is the dielectric constant, is 2.3. Distance D between the plates is given in centimeter, which when converted is 1 times 10 to the power minus 2 meter. A, that is the area, is 200 cm squared, which is converted to meter as 200 times 10 to the power negative 4 meter squared. V is 3000 volts. And of course, permittivity of free space is 8.85 times 10 to the power negative 12. So with this, we can recall our formula for capacitors with dielectric, so that the capacitance will be expressed as K, A naught A over D, which is 2.3 times 8.85 times 10 to the power negative 12 times 200 times 10 to the power negative 4. The units have been excluded to avoid confusion. Divided by the distance, which is 1 times 10 to the power negative 2 meters, which leaves us with 4.071 times 10 to the power negative 11 farad. For the second part, that is part B, we are to find the charge flowing through the capacitor. Recall that C is equal to Q over V, which leaves us with Q is equal to CV. C has been calculated from I as 4.01071 times 10 to the power negative 11 farad, and the voltage is 3000 volts. So that our Q is approximately 1.22 times 10 to the power negative 7 coulomb. And then we want to find the work done in charging the capacitor, and that is W is equal to half CV squared. So that W is 1 over 2 times C, 4.071 times 10 to the power negative 11 times 3000 squared. This leaves us with approximately 3.66 times 10 to the power negative 4 joules. Then the fourth question says we should calculate the new energy stored in the capacitor if the potential difference is tripled and the capacitance remains constant. If the potential difference is tripled, it means our new potential difference will be 3V, which is 3 times 3000. And so our new voltage is 9000 volts and the capacitance remains constant. So that W, which is the work done or the energy stored, is equal to 1 over 2 times the capacitance, which is kept constant, multiplied by 9000 squared. This leaves us with about 1.627 times 10 to the power negative 3 joules. which can approximate to 1.63 times 10 to the power negative 3 joules. This answer is to two decimal places rather. 2 decimal places. So I've come to the end of this particular lecture. Remember to like my videos, share my videos, and of course, drop your comments in the comment sections. Thank you.